All right, so we're going to look at integration by parts. We're going to do it with an area analogy. Always like to be able to draw a picture of some sort, and I think our integration by parts can be quite confusing when it's just written algebraically. So let's break it down. So the first thing I want us to imagine is that we have a rectangle, and it has an area equal to u times v. But these are not just any. This is not just any rectangle. This rectangle has a length of u, where u is a function of some other parameter x. So u is a function in itself, and all the same is true for v. So v is also a function of x. And so what we want to start to understand is, as we change the area of this rectangle, how does the area change? So that's our first question. So the first question is to say, all right, consider if we were to put on some horizontal strip that has a width of u. You can see it has a width of u, which is this length here, which is equal to this length, and it's some small change in v. And similarly, if we put in a vertical strip in pink here, that's going to have dimensions v du. So we're sort of growing our rectangle by adding these small strips on the side. I encourage you to think about what the area of this section might be. But I think you would agree, given everything here, that this would be dv multiplied by du. And when we're doing integration, this is actually going to be negligible. It's going to be so small that we can actually ignore it. So we've left that out for now. But what we want to do now is we just want to consider this. So we want to consider the change in area of this rectangle. And so we might write it like this to begin with. We'd say, all right, how does this rectangle change? Well, we'd say that the area changes. We can notate that as d, the derivative of u times v. And the way it's changing is the sum of the horizontal and vertical contributions. So we can say that u dv is the horizontal contribution and v du is that vertical contribution. And so what we have is this situation where we've got a derivative on the left-hand side, and then we've got the sum of these two products on the right-hand side, where they represent this small change in the area of the rectangle. And then what we can do is we can actually take the integral of both sides, and that's going to give us this. If you take the derivative of the integral of the left-hand side, then that the integral of a derivative, well, they're inverse operations, right? So they're going to cancel out. And then on the right-hand side, you're taking the integral of u dv, and then you're going to add on the integral of v du. Now, in one sense, we've taken the integral of the whole right-hand side and then we've broken it up. But remember, the integral of a sum is the sum of the integrals, so we're allowed to do that. And so what we do is we're going to end up with integration by parts, which is, here it is in all its glory. You get the integral of u dv is equal to uv minus the integral of v du. And remember that u and v are functions of x. So the reason that integration by parts is useful is because if we have integrals of the form where we have a function multiplied by a derivative, and sort of we can see that in the function or in the integral that we need to take, then we are able to use this property to find that integral. So let's have a look at how we might do that. So if we jump over to look at an example, here's something we might be asked to integrate. So integrate or solve the integral of x cos x dx. And at the top there, we just have what we learnt before, which is integration by parts. So it's the integral of u dv is equal to uv minus the integral of v du. Okay, and so you're probably wondering, how do we actually apply this? Well, the first thing we're going to do is we're going to look at the structure of the thing we need to integrate, which is x multiplied by cos x. And we're going to say to ourselves, we're going to make some strategic choices. So we're going to choose u to be equal to x, because that's easy to differentiate. And we're then going to take dv be equal to cos x dx, so that integration by parts can be applied smoothly. So basically, let u equal x and dv equal cos x dx. I should say that if we just rearrange this term here, dv equals cos x dx, it'd be dv dx equals cos x. And so let me show you what I mean by that. We have this. So u equals x, dv dx equals cos x. And so that implies, if we were to take the integral of both sides, that v equals sine x. And so what we can do now is we can apply our integration by parts. And we can see this. So we get x sine x, which is u multiplied by v. V minus the integral of sine x dx. Remember, sine x is v, and du is 1. The integral of u with respect to x here is 1. So this just turns out to be sine x. And now this is manageable. We can say that following integration by parts, we can get our final answer here, because we know that the integral of sine x is negative cos x. So we get that the integral of x cos x dx is equal to x sine x plus cos x plus that constant of integration. Okay, if we're just thinking in terms of these functions and maybe relating it a little bit to that previous analogy we had, if we were to draw this, this is our original rectangle. So this is our u times v, which was equal to x sine x, remember. So u was x and v actually turned out to be sine x. And so the area of the rectangle, remember, was made up of those vertical and horizontal contributions to make the total area. So if we sketch the next part, we get u dv. Okay, so u dv is equal to x multiplied by cos x. Okay, and so we get v du is equal to v, which is sine x, du is 1. So we just get v du is sine x. And so what we get is a situation where if you were to take definite integrals of x sine x between, say here and its first x-intercept, then you could just sum up the areas of this top pink function between here and here, and this blue function between those 2 points as well, between that point there. And then that will tell you the area under the curve. So yeah, hopefully you found that interesting. If you did, give us a thumbs up. Let us know if you need any private tutoring, and good luck with everything you're doing. I'll talk to you soon.